93 billion light-years of space, hundreds of billions of galaxies, and inside each one, hundreds of billions of stars. The math says life should be everywhere, so why has nothing ever called back? We've been scanning the sky for signals since 1960. Complete silence. We're going to look at the impossible scale keeping us apart, the theories about civilizations that vanished, and the stranger idea that something out there is choosing to stay quiet. If you want more videos like this, subscribe and hit like. It helps more than you know. Stay awake. We begin. Picture 400 billion stars packed into a single spinning disk. That's our galaxy alone. Scientists estimate there are billions of planets inside it, sitting at just the right distance from their star to hold liquid water on their surface. Billions. Inside one galaxy. Now multiply that across 2 trillion galaxies spread across the observable universe. The math is overwhelming. Life should be everywhere. Signals should be crossing the sky constantly. Ships should have passed through our solar system long before humans ever looked up at the stars. And yet, silence, total, complete silence. No signal, no ship, no artifact, no proof of anyone. That silence is one of the strangest facts in all of science. And it has a name. Physicists call it the Fermi paradox. But the story behind it is even better than the name. In the summer of 1950, a group of brilliant scientists walked to lunch at Los Alamos Laboratory in New Mexico. They were joking around, talking about a cartoon that had run in a magazine that week. The cartoon showed aliens stealing garbage cans from New York City streets. Everyone laughed. Then the conversation shifted. Someone brought up the probability of faster than light travel. The group started throwing ideas around, estimating odds, crunching numbers the way scientists do even when they're off the clock. Then a man named Enrico Fermi went quiet for a moment. He looked up and asked a question so simple it almost sounded like a joke. Where is everybody? The table went silent because Fermi had just done the math in his head, and the answer made no sense. Fermi was one of the sharpest minds of the 20th century. He had built the world's first nuclear reactor. He could calculate the size of a distant explosion using nothing but a handful of torn paper falling through the air. His instincts were legendary, and his instinct in that moment said something was deeply wrong. He reasoned like this: the galaxy is ancient. Our star formed roughly 4.5 billion years ago, but the Milky Way has been producing stars for over 10 billion years. Some of those stars are billions of years older than ours. If life developed around even a fraction of them, those civilizations had a massive head start. Even travelling at speeds far below the speed of light, a civilization with a billion-year advantage could have spread across the entire galaxy many times over by now. So where are the ships? Where are the signals? Where is any trace of anyone? The question ate at scientists for years. It still does. Because no one has found a satisfying answer. Some researchers thought Fermi was asking the wrong thing. Maybe civilizations rise and fall so fast they never get the chance to spread. Maybe the distances are simply too brutal. Maybe they're out there and we're just too primitive to notice. But here's what makes the paradox genuinely unsettling. It doesn't require aliens to be everywhere. It only requires one civilization in 10 billion years to have sent even a single probe toward the stars. That probe's descendants should have reached us by now. And nothing has arrived. Every time astronomers point a radio telescope at the sky, they hear static. Every time a search program scans thousands of stars for structured signals, the results come back empty. We've been listening since 1960, checking star after star, and the universe keeps returning the same answer. Quiet. What Fermi sensed at that lunch table was a crack in reality. The numbers say one thing, the sky says another. And the gap between those two answers might be the most important mystery humans have ever faced. Something is wrong with our picture of the universe, and figuring out what might change everything we think we know about our place in it. The first clue starts with something almost impossible to picture. The sheer size of the space between us and everyone else. Stand outside on a clear night and look up. Every star you can see with your bare eyes sits within a few thousand light years of Earth. That sounds far. It is far, but compared to the full size of our galaxy, what you're seeing is barely your own backyard. The Milky Way stretches 100,000 light-years from one edge to the other, 100,000 years of travel at the fastest speed the universe allows. Our entire recorded human history, every empire, every war, every civilization, fits inside about 5,000 years. We would need to repeat that history 20 times just to cross our own galaxy at the speed of light. And our galaxy is one of the smaller ones. The nearest large galaxy to our own, a giant spiral called Andromeda, sits about 2.5 million light-years away. A signal travelling at the speed of light, sent from Earth today, would arrive there in 2.5 million years. Our entire species has only existed for about 200,000 years. We would have to evolve, go extinct, and be replaced by whatever comes after us many times over before that signal ever arrived. Now step back further. The observable universe, the portion of space we can actually detect, stretches about 93 billion light-years across. Inside that bubble sit roughly 2 trillion galaxies. 2 trillion. If you tried to count them at 1 per second, it would take 60,000 times longer than the current age of the universe to finish. Most of those galaxies will never be reachable. Ever, the universe is expanding, and the galaxies near the edge of our observable bubble are already moving away from us faster than light can chase them. That means right now, as you listen to this, the majority of the universe is permanently sealed off, locked behind a wall that grows faster than anything can cross it. Picture it this way. Imagine you're standing in the middle of a field. The field is the universe. You can see in every direction for maybe half a mile before the fog rolls in. That half-mile circle is everything your telescopes can ever reach. Everything outside the fog is gone forever, accelerating away, unreachable, invisible, and inside your half-mile circle, the distances between any 2 points where life might exist are still measured in thousands and millions of light-years. The scale makes communication nearly impossible and physical travel almost laughable with any technology we currently possess. Our fastest spacecraft, the Voyager probe, has been flying away from Earth for over 45 years. At that speed, it would take about 70,000 years to reach the nearest star system to our own. 70,000 years for the nearest one, out of 400 billion in just our galaxy alone. Here's the number that really lands. That nearest star system, called Alpha Centauri, sits just over 4 light-years away. 4 light-years sounds manageable until you remember that 1 light-year equals about 6 trillion miles. The distance to Alpha Centauri is roughly 25 trillion miles. If the Earth were the size of a basketball and Alpha Centauri were placed at the same scale, it would sit somewhere in the middle of Asia. Our fastest probe would cross that distance at the speed of a slow crawl. This is the first wall between us and anyone else out there. Pure, brutal, unforgiving distance. It doesn't care about our technology or our ambitions. It simply exists, massive and silent, the same way it has for billions of years. But what the distance doesn't explain is why we hear nothing at all. Even across these gaps, signals should be crossing the sky. So why aren't they? The answer has to do with something even harder to fight than distance. Every civilization in the universe, no matter how advanced, runs into the same wall, a hard limit baked into the laws of physics itself. Nothing can travel faster than light. No ship, no signal, no information of any kind. That rule sounds simple. Its consequences are devastating. Light moves at 186,000 miles per second. In a single second, it crosses a distance equal to circling the Earth 7.5 times. In 8 minutes, it travels from our star to Earth. It reaches the edge of our solar system in about 11 hours. Those numbers feel fast. Against the galaxy, they become almost laughably slow. A radio signal, which travels at the same speed as light, takes 100,000 years to cross the Milky Way from one side to the other. 100,000 years. If a civilization on the far edge of our galaxy sent us a message the moment modern humans first appeared on Earth, that message would still have 90,000 years left to travel before reaching us. We wouldn't hear it for 90,000 more years. And here's where it gets stranger. Even if we did receive a message, and even if we sent one back immediately, that reply would take another 100,000 years to arrive at the source. The full round trip spans 200,000 years. Longer than our species has existed. Any conversation across galactic distances becomes something almost impossible to imagine. You send a word. 200,000 years pass. You receive a reply. Your civilization has risen and collapsed and maybe risen again multiple times before the conversation even begins. This is why radio silence doesn't automatically mean we're alone. It might mean that the messages are in transit right now, crawling toward us across the dark, and simply haven't arrived yet. But there's a harder version of this problem. Even if a civilization nearby sent a signal 1,000 years ago, targeted directly at Earth, we only started listening in 1960. Before that, we had no equipment capable of detecting it. That signal could have swept past our planet and we would have noticed nothing. We had ears for 60 years out of a galaxy that has been operating for 10 billion. Our radio bubble, the sphere of signals we broadcast outward from Earth, stretches only about 100 light-years in every direction. 100 light-years sounds like a lot. Inside a galaxy 100,000 light-years wide, it's a rounding error. A marble sitting inside a football stadium. Any civilization more than 100 light-years away has received zero proof that we exist. To the vast majority of the galaxy, Earth is still a silent planet. No indication of technology, no indication of intelligence, just a quiet little world orbiting an ordinary star in an unremarkable corner of the Milky Way. Now turn that round. We've been scanning the sky for signals since 1960. Our equipment has improved enormously in that time. But 60 years is nothing. If a civilization broadcast a signal for 10,000 years and then went quiet, we might have started listening 100 years too late. The universe operates on timescales that make human history look like a blink. The speed of light, despite being the fastest thing that exists, is still maddeningly slow against those timescales. Physics built a prison. Every civilization sits inside it. And the bars are made of something that can't be broken, bent, or bought off. What's strange is that despite knowing all this, the silence still surprises scientists. Because the galaxy is old enough that signals should have had time to pile up. The fact that none have arrived suggests something deeper is going on. Something that has to do with how rare the right conditions for life actually are. 400 billion stars. That's the low estimate for the Milky Way. Some astronomers push the number closer to 400 billion on the high end, others place it near 100 billion on the low end. Either way, the count is so large, it stops feeling like a number and starts feeling like a concept. A concept that makes the silence more confusing, not less. Because stars aren't alone in space. Most of them carry planets. Data from space observatories suggests that on average, each star in our galaxy hosts at least one planet. That puts the planet count in the Milky Way somewhere around 100 billion to 400 billion worlds. Among those worlds, scientists estimate that billions fall inside what researchers call the habitable zone, the orbital distance where liquid water can exist on a planet's surface. Water is the key ingredient in every form of life we know about. Billions of worlds with the right conditions for liquid water. In one galaxy. And yet the sky is quiet. Here's the part that scientists keep returning to. Among those billions of potentially habitable worlds, even if life only developed on a tiny fraction, 1% of 1%, that still leaves tens of thousands of worlds where biology got started. And if even a small fraction of those went on to produce intelligent species, the number of civilizations that should have existed across the Milky Way's 10 billion year history is enormous. Even the most conservative estimates suggest we shouldn't be alone. But we seem to be. Some researchers tried to put a number on it. A group of scientists ran estimates based on stars similar to ours in age and size. They identified billions of candidates. They narrowed that list by planets at the right distance. They narrowed it further by estimated atmospheric conditions. The final count of worlds that could support complex life still ran into the tens of millions within our galaxy alone. Tens of millions, and we've heard from zero of them. One of the most striking examples of this gap sits less than 500 light-years from Earth. The Kepler Space Telescope spent years staring at a single patch of sky, watching for tiny dips in starlight caused by planets passing in front of their stars. It found thousands of planets in that one small slice of the sky, thousands of worlds we never knew existed, revealed in a few years of looking. The universe is clearly full of planets. The raw ingredients for life are everywhere. Carbon, hydrogen, oxygen and nitrogen are among the most common elements in the cosmos. The chemistry needed for biology isn't exotic, it's standard. And still, nothing. Scientists call this the numbers problem. The math points toward a universe crowded with life. The observations point toward a universe with exactly one civilization we know of. Ours, the tension between those two facts doesn't go away the more you look at it. It gets worse. Because it's not just that the universe seems empty. Certain conditions are required for life to move beyond simple bacteria and develop into something that builds technology and asks questions. And when scientists started looking closely at those conditions, they realized the universe is far more selective than anyone had hoped. The planet count is staggering. But having a planet is just the beginning of a very long, very brutal checklist, and almost nothing passes it. The details of that checklist are far stranger than anyone expected. The summer of 1950 was ordinary in most ways. The Korean War had just started. Television was spreading across American homes. Scientists at Los Alamos Laboratory in New Mexico were working on problems that shaped the Cold War. And on one ordinary afternoon, a group of them walked to lunch and changed how humanity thinks about its place in the universe. The man who started it was Enrico Fermi. He was already a legend by that point. In 1942, he had built the first nuclear reactor in a converted squash court under the bleachers at the University of Chicago. During the Manhattan Project, his colleagues called him the Pope because his instincts were so reliably correct. But Fermi's real gift wasn't building things. It was a technique called estimation. He could calculate an answer to an almost impossible question using only basic logic and a few known facts. He once estimated the size of a nuclear explosion by dropping pieces of torn paper from waist height, watching how far the blast wave pushed them sideways, and doing the math in his head. His estimate landed remarkably close to the real measurement. That same instinct hit him at lunch. The conversation started with a magazine cartoon about aliens stealing garbage cans from New York. The scientists joked about it. Then someone brought up recent news stories about unexplained aerial sightings over the United States. The group speculated. Could any of those reports be real? How likely was faster than light travel? What would it take? Fermi stayed quiet. He was thinking. And then, between bites of his meal, he looked around the table and said it. Where is everybody? His colleagues knew exactly what he meant. In 3 words, Fermi had compressed a massive logical problem into something inescapable. If the galaxy is this old, and if life is a natural outcome of chemistry, then civilizations should have had billions of years to develop. Even at speeds far below the speed of light, a civilization with enough time could colonize the entire galaxy. It would take perhaps a few million years at most, a blink compared to the galaxy's 10 billion year age. So where are the colonies? Where are the signals? Where is any evidence that anyone, anywhere got there first? The table had no good answer, and the scientific community has been wrestling with that question ever since. What makes Fermi's paradox powerful is that it doesn't require aliens to be common. It requires only one civilization somewhere in 10 billion years, to have survived long enough to spread. Just one. And that one civilization's fingerprints should be visible by now. They aren't. Researchers have proposed dozens of explanations. Maybe life is rarer than we think. Maybe intelligent species destroy themselves before they reach the stars. Maybe the universe is full of life, but everyone is hiding. Maybe we're simply not recognizing the signals we receive. Every explanation carries problems. Every answer opens new questions. And the original question, the one Fermi asked over lunch with a handful of colleagues in New Mexico, still has no clean answer more than 70 years later. What came after Fermi was an attempt to do something ambitious, to put actual numbers on the probability of alien life, to turn the paradox from a feeling into a calculation. That attempt became one of the most famous equations in history, and it produced answers that ranged from hopeful to terrifying, depending on how you ran the math. In the fall of 1961, a young astronomer named Frank Drake stood in front of a room full of scientists at a conference in West Virginia and wrote an equation on a blackboard. It had 7 variables. Nobody in the room had solid values for most of them. That didn't stop the equation from becoming one of the most debated pieces of math in the history of science. Drake had been part of the first serious attempt to listen for alien radio signals, a project called Ozma, named after the princess in the Wizard of Oz stories. For months, he had pointed a large radio telescope at 2 nearby stars and listened. He heard nothing meaningful. But the experience sharpened his thinking. If we're going to search, he reasoned, we need to know what we're searching for. We need an estimate. We need to know how many civilizations might realistically be out there right now, broadcasting signals we could detect. So he built an equation to figure it out. The Drake equation multiplied a chain of probabilities together. It started with the rate at which new stars form in our galaxy every year. Then it asked what fraction of those stars have planets. Then what fraction of those planets could support life. Then what fraction actually develop life. Then what fraction of those go on to produce intelligent species. Then what fraction of those develop technology capable of sending signals. And finally, how long those civilizations survive and keep transmitting. The idea was simple. Chain enough factors together and you get a rough estimate for how many civilizations are broadcasting right now. At the first conference where Drake presented it, the group of scientists filled in rough guesses for each variable and got an answer somewhere between 1,000 and 100 million civilizations in the Milky Way alone. The range was enormous, but even the low end seemed exciting. For decades, scientists used the equation to argue that we lived in a crowded galaxy. The universe had been running long enough, stars were plentiful, planets were common. Life seemed like a natural result of chemistry. The numbers kept pointing toward company. But the equation had a weakness hiding in plain sight. Most of its variables were pure guesses. Nobody actually knew what fraction of planets develop life, or how long civilizations typically survive. The equation could produce any answer depending on what you plugged in. Optimists ran it and got millions of civilizations. Pessimists ran it and got just one. That one was us. The equation became famous partly because of what it revealed and partly because of what it exposed. It made the question precise. It forced scientists to admit exactly which pieces of information they were missing. And it highlighted just how much uncertainty was hiding inside the seemingly confident claim that life must be everywhere. The real work happened in the decades after Drake wrote it. Scientists spent years trying to nail down actual values for each variable using telescopes, biology experiments, and astronomical surveys. Some of the variables became clearer over time. Others remained stubbornly unknown. And in 2024, a group of researchers took another serious look at one of the most uncertain variables in the equation: the fraction of planets where the right conditions for intelligent life actually arise. Their answer shook the field. The number was far smaller than anyone had hoped, and it changed the mood around the Fermi paradox from cautious optimism to something closer to dread. For decades, scientists ran the Drake equation with generous assumptions. Life seemed likely. Intelligence seemed like a natural endpoint. The galaxy felt full. Then, in 2024, a team of researchers revisited one of the most critical numbers in the equation: the probability that a planet with life goes on to develop intelligent, technologically capable beings. Their answer? Somewhere between 0.003% and 0.002%. Read that again. Even on the optimistic end, only 2 planets out of every 1,000 with life on them eventually produce a species capable of building a radio telescope. The study focused on something specific: plate tectonics, the slow grinding movement of a planet's crust, the same process that builds mountains and pulls continents apart on Earth. Scientists have known for years that plate tectonics plays a huge role in regulating Earth's climate, recycling carbon, and keeping the planet's chemistry stable over billions of years. Without it, Earth might have cooked itself long ago or frozen solid. The problem is that plate tectonics appears to be rare. Most rocky planets we've observed seem to have rigid, locked crusts. No movement, no recycling, just a static surface slowly being bombarded by radiation and volcanic gases with no mechanism to reset. Earth's plate tectonics may have been the product of a very specific combination of factors: the planet's size, its interior temperature, its water content, and possibly even the giant collision early in Earth's history that formed the Moon. Change any of those details and Earth might have no moving plates. Remove the plates and you likely remove intelligent life. But the 2024 study went further. It also examined the timing required for intelligence to emerge. Life appeared on Earth relatively quickly after the planet formed. But complex, large-brained animals took billions of years longer. That long runway required geological stability, a stable climate. A planet that didn't swing between extremes every few million years. That kind of stability, the study argued, is itself a product of a very specific and very rare set of circumstances. So the math shifted. Suddenly, the galaxy's billions of potentially habitable worlds started to look different. Many of them probably developed simple microbial life, tiny, single-celled organisms that never moved beyond the bacterial stage. The gap between a microbe and a creature capable of wondering about its own existence is enormous. And the conditions required to cross that gap may be nearly impossible to meet. This doesn't mean we're alone. 0.002% of billions of planets still leaves room for thousands of other intelligent species to have existed somewhere in the Milky Way. But it explains part of the silence. And it raises a more uncomfortable question. If the conditions are this demanding, and if we somehow met all of them here on Earth, does that make us a cosmic accident? A fluke? A product of so many specific circumstances lining up that the odds of it happening twice in the same galaxy, at the same time, in listening range of each other, become very small. Scientists debate this daily, but what the 2024 update didn't touch was something even larger than rare conditions. A force operating at the scale of the entire universe that has been quietly working against life ever since the beginning. It's already reshaping the cosmos. And there's nothing any civilization can do to stop it. Imagine waking up one morning and discovering that the walls of your room are moving outward. Slowly, silently, but constantly. And every day they move a little faster. By the time you realize what's happening, the walls are already so far away that you can't see them anymore. That is roughly what is happening to the universe. Space itself is expanding. Every galaxy is moving away from every other galaxy, carried apart not because they're flying through space, but because the space between them is physically stretching. The distance between two galaxies grows without either of them moving at all. This has been happening since the beginning of the universe, about 13.8 billion years ago. For the first several billion years, scientists expected the expansion to slow down. Gravity pulls things together. Eventually, gravity should have started winning. It never did. In 1998, Two independent teams of astronomers studying distant exploding stars discovered something that overturned everything. The universe wasn't slowing down, it was speeding up. The expansion was accelerating, and had been for roughly 5 billion years. Something was pushing space apart faster and faster. Scientists gave that something a name: dark energy. They have no idea what it actually is. They know it exists because they can measure its effects, but its nature remains one of the deepest unsolved problems in physics. What they do know is this: dark energy makes up roughly 68% of everything in the universe. The ordinary matter that makes up stars, planets, and people accounts for less than 5%. The universe is mostly made of something we can't see, can't touch, and can't explain, and that something is actively tearing the cosmos apart. For any civilization hoping to communicate with others across the universe, this is catastrophic. As space expands, the light travelling between galaxies has to cross a larger and larger distance. Eventually, distant galaxies are moving away faster than light itself can cross the gap. Their light never arrives. They become permanently invisible. Scientists have calculated that we are already past this point with a large portion of the universe. Billions of galaxies that technically exist are already gone from our view forever. Their light started travelling toward us long ago, but will never arrive because the space it has to cross keeps growing faster than it can travel. The universe is shrinking our observable neighbourhood in slow motion. For a civilization trying to listen for signals from across billions of light years, this means the window is closing. Every billion years that passes, more of the universe locks itself behind that invisible wall. The universe that existed in the past, when it was younger and smaller, offered better chances of contact. The universe of the future offers fewer. We arrived at a specific moment in cosmic history, neither too early nor too late. But the expansion is relentless, and it has been working against the idea of cosmic community from the very beginning. And what's already happened to entire galaxies, slipping silently behind that horizon forever, is just a preview of something even stranger ahead. Right now, billions of galaxies are crossing a line. Once they cross it, they are gone. Their light, which has been travelling toward us for billions of years, will never arrive. The space between us and them is expanding too fast. Those galaxies will exist somewhere in the universe, but we will never see them, never hear them, and never know what might have lived there. Scientists call this boundary the cosmic horizon. It's not a physical wall. You can't fly toward it. It moves with the expansion of space itself, and anything that crosses to the other side of it becomes permanently unreachable. The universe we can observe today, that 93 billion light-year bubble we discussed earlier, is already smaller than the universe that existed when it was young. In the future, it will be smaller still. Hundreds of billions of years from now, the Milky Way and a handful of nearby galaxies will be all that remains visible. Everything else will have vanished behind the horizon, invisible and unreachable forever. Think about what that means for life. If any civilizations exist in those distant galaxies right now, we will never know. If they are broadcasting signals, those signals are already unable to reach us. The separation is permanent, and this erasure is already happening. Astronomers have identified a region of space where the galaxy count begins to drop sharply. Beyond a certain distance, we stop seeing galaxies where we expected to see them. The universe beyond our horizon is already emptying itself from our view in real time. Here is what makes this genuinely strange. The light we see from distant galaxies is old. When astronomers look at a galaxy 2 billion light-years away, they see it as it was 2 billion years ago. Some of the galaxies visible in our best telescopes today might already be dead. Their stars burned out. Their planets went dark. And we are watching their ancient light and calling them alive. It's like looking at photographs of people who have long since passed away. The image is real, the subject is gone. If a civilization existed in one of those distant galaxies 2 billion years ago and sent us a signal, That signal might be travelling toward us right now. But if that galaxy has already crossed our horizon, the signal faces a losing race against expanding space. Some signals, sent long ago from places that have since crossed the boundary, will simply run out of reachable universe before they get here. The universe is not just silent. It is actively becoming less knowable with each passing billion years. For the search for other life, this creates a hard deadline that no technology can push back. The window for finding anyone outside our local neighbourhood of galaxies is not just closing, it is almost closed. In cosmic terms, we are arriving at the party as the lights are going out. What could drive this kind of ruthless erasure? A force so dominant it shapes the fate of everything in the cosmos. Scientists found it, and understanding what it is makes the question of alien life feel even more urgent. 68% of the universe is made of something nobody understands. Scientists call it dark energy. They can't see it, can't collect it, and can't explain what it actually is. But they know it's real because it's doing something visible, pushing everything in the universe apart faster and faster every single year. Here's how they figured it out. In the 1990s, two teams of astronomers were studying a specific type of exploding star called a Type 1a supernova. These explosions are useful because they always release almost exactly the same amount of light. That makes them cosmic measuring sticks. By comparing how bright these explosions appear to how bright they should be, astronomers can calculate how far away they are. What they found made no sense. The distant explosions were dimmer than they should have been, much dimmer. That meant they were farther away than the models predicted. The universe had been expanding faster than gravity should have allowed. Something was pushing space outward, and that something was growing stronger over time. Both teams published their results in 1998. They fully expected the other group to find the error in their work. Instead, both teams had found the same thing independently. The discovery eventually earned a Nobel Prize. Dark energy doesn't just make the universe expand. It makes the expansion speed up over time. And because it appears to be a property of space itself, the more space there is, the more dark energy there is. The more dark energy there is, the faster the universe expands. The faster the universe expands, the more space is created. It feeds itself. For any civilization trying to make contact with others, dark energy is the ultimate enemy. It guarantees that the universe grows less reachable with every passing era. Signals that could have crossed the universe in its youth face a longer and longer journey now. In the far future, they'll face a journey that can't be completed. Some physicists have described dark energy as the universe deleting its own address book. Every billion years, more cosmic neighbourhoods fall off the edge of what can be contacted. What's especially strange is that we have no idea if dark energy is constant or if it changes over time. Some theories suggest it might eventually grow so strong that it tears galaxies, stars, and even individual atoms apart in an event called the Big Rip. Others suggest it will remain at its current level indefinitely. Either way, it ensures that civilizations across the universe are drifting further apart every day, locked behind walls of space that grow thicker with every passing year. Dark energy doesn't care about biology. It doesn't discriminate between planets with life and planets without. It simply expands space and pushes everything apart with complete indifference. But here's the part that scientists find deeply unsettling. Even without dark energy, even in a universe that stayed the same size, the evidence for other civilizations is missing. The problem isn't just that space is expanding. Something else is wrong. Some researchers think that something is far more personal. A filter, a wall, a barrier that stops nearly every species before it ever gets to the point of sending signals across the galaxy. And the worst part is that we might not have passed it yet. Somewhere between the formation of a planet and the moment a species starts transmitting signals into space, something goes wrong. Almost every time. That's the core of an idea called the Great Filter. and it's one of the most disturbing concepts ever proposed in the search for alien life. The logic is simple. We know the universe is old. We know it has billions of potentially habitable planets. We know life emerged on at least one of them. But we see no evidence of any civilization beyond our own. The universe looks empty of intelligence. So something must be stopping civilizations from reaching the point where we'd be able to notice them. That something is the great filter. A barrier. A step in the process of developing from chemistry to complex life to spacefaring civilization that almost nothing ever manages to cross. The concept was sharpened by economist Robin Hanson in the late 1990s. Hanson laid out the problem clearly. For the universe to look the way it does, something must filter out civilizations somewhere along the path. The question isn't whether the filter exists, the question is where it sits. If the filter is behind us, we might be safe. The hardest step might already be done. The emergence of complex life, or the development of intelligence, or the invention of technology might be the filter. We got through it. Most others didn't. If the filter is ahead of us, the situation is very different. It means that civilizations routinely reach our level of development and then fail to make it further. Nuclear war. Climate collapse. Resource depletion. A pandemic that wipes out global society before interstellar communication is possible. Some pattern of self-destruction that catches almost everyone. And here is the part that keeps researchers up at night. Right now, we can't tell which one it is. The universe's silence is the same whether the filter is in our past or our future. Either way, no civilizations make it to the stars. The sky stays quiet. So researchers look for clues. If the filter is behind us, we'd expect life to be rare. Finding that even simple microbial life is absent on Mars, Venus, or the moons of Jupiter would actually be good news. It would suggest that the hard step, getting life started at all, is what most planets fail at. We'd be lucky survivors of an almost impossible beginning. But if we discovered life elsewhere in the solar system, even bacteria, that would be terrifying. It would mean life starts easily. Which means the filter isn't in that early step. It's somewhere closer to us. Somewhere still ahead. Every mission searching for life on Mars carries this hidden weight. Finding nothing there might be the best possible news for humanity's long-term survival. Finding something simple and microbial might mean we're already on borrowed time. The filter doesn't announce itself. It doesn't leave a warning sign. Civilizations that ran into it are gone. They can't report back. And what most scientists agree on is this. The filter is real. Something is stopping civilizations. The galaxy should be full of signals, and isn't. The question is whether the hardest part is something we already went through billions of years ago, quietly without knowing it. Life appeared on Earth fast, astonishingly fast. The planet formed about 4.5 billion years ago. For the first several 100 million years, it was being bombarded constantly by asteroids. The surface was half molten. The atmosphere was toxic. Conditions were hostile to almost any chemistry we know of. And yet, by about 3.8 billion years ago, there were already bacteria on Earth. Simple, single-celled organisms, the earliest life we have evidence of, appeared within a few 100 million years of the planet becoming even barely livable. By cosmic standards, that's a near-instant start. Life hit the ground running. Then it stopped. For nearly 2 billion years, life on Earth stayed almost exactly the same. Bacteria, single cells. Simple chemistry. The oceans were full of microscopic life, but nothing complex appeared. No multicelled organisms, no animals, no brains. Just a global ocean of tiny organisms going through the same basic routines for longer than the age of our entire solar system. That pause is called the Great Oxygenation Event Era and the Proterozoic, but the important idea is simpler than the name. Life hit a wall it couldn't cross for an almost unimaginable length of time. The wall was a step called the eukaryotic cell. Unlike bacteria, which carry their genetic material loose inside the cell, a eukaryotic cell has a nucleus, a protected command center wrapped in its own membrane. This structure allowed cells to become far more complex. It made everything that came after possible: plants, fungi, animals, human brains. But making a eukaryotic cell required one bacterium to absorb another, and then, instead of destroying it, form a permanent partnership with it. That merger had to happen in exactly the right way, at exactly the right time, with exactly the right biological chemistry. Scientists studying this event think it may have happened exactly once in Earth's entire history. Once, all complex life on Earth, every animal, every plant, every organism with more than one cell, descends from that single event. If it hadn't happened, Earth might still be a world of bacteria today, and it might remain that way for another 4 billion years until our star expands and swallows the planet. This is one of the strongest candidates for the Great Filter. The leap from simple cells to complex cells is so improbable that on most planets with life, it may simply never occur. Those planets stay microbial forever. They never produce anything that asks questions, builds telescopes, or wonders about the universe. If that's true, the galaxy may be full of oceans teeming with bacteria and almost nothing else. Simple life everywhere, complex life nearly nowhere. And if that one merger had never happened here, we wouldn't be here to notice. But the eukaryotic cell wasn't the only improbable step. What happened after it took almost another billion years? And it required a set of conditions so specific that most planets may never have them. Take a planet. Give it the right temperature. Fill it with water. Seed it with chemistry that produces life. Follow all the steps correctly. Do everything right. It still might produce nothing but bacteria for billions of years. And here's why. Earth's surface is broken into massive plates of rock, like cracked pieces of an enormous shell. Those plates grind against each other, slide under each other, and slowly move across the planet's surface. Where they collide, mountains rise. Where they pull apart, new ocean floor forms. Where one dips under another, volcanic chains appear. This movement is called plate tectonics, and scientists now believe it was one of the critical ingredients that allowed intelligent life to develop here. Plate tectonics does something crucial for a living planet. It acts like a thermostat. Carbon dioxide, the gas that traps heat and warms atmospheres, gets released by volcanoes at one end and pulled back into the Earth at the other. Rocks weathered by rain absorb carbon dioxide from the atmosphere. Those rocks eventually get pulled underground by the moving plates. The carbon gets recycled. The process regulates the planet's temperature over millions of years, keeping it stable enough for complex life to survive and evolve. Without that regulation, small shifts in the planet's orbit or variations in the star's energy output can spiral into runaway heating or freezing. A planet without plate tectonics lacks the mechanism to correct those swings. Venus is a nearby example. It has a similar size and composition to Earth, but it appears to have a rigid crust with no active plate movement. Today it has a surface hot enough to melt lead and an atmosphere crushing enough to crumple a spacecraft. Whatever chance it had at complex life seems long gone. Mars sits on the other end. It lost most of its plate activity billions of years ago. Its atmosphere thinned out, its magnetic field weakened. Radiation from the star bombarded its surface. Whatever water it once had was stripped away or froze underground. Earth kept going, plates kept moving, the carbon cycle kept running. The climate stayed within a range that allowed multicellular life to develop, persist, and eventually grow brains. Here's the uncomfortable part. When scientists look at rocky planets in other star systems, they see no clear signs of plate tectonics. Detecting it from light years away is extremely hard. But models suggest that the conditions required for active plate movement, a planet of the right size, the right internal temperature, the right amount of water, the right early history, are surprisingly specific. Many planets are too small to hold enough internal heat to drive plate movement. Many are too large, locking their crusts rigid under immense pressure. Some have the right size, but the wrong composition. Getting a planet that stays geologically active for billions of years on end may be far rarer than the raw count of rocky worlds suggests. Add this requirement to the others, and the list of what's needed for intelligent life keeps growing longer. The right star, the right orbit, the right size, the right internal structure, the right history. Each condition narrows the field dramatically. And there's one more factor that scientists added to this list recently. Something that sounds almost too specific to matter. But without it, Earth's story might have ended before it truly began. About 4.5 billion years ago, when the solar system was young and still chaotic, something hit Earth. A planet roughly the size of Mars came out of nowhere and slammed into the young Earth at a shallow angle. The collision was catastrophic. It vaporized huge chunks of both worlds. A ring of debris was blasted into orbit around Earth. Over millions of years, that debris coalesced into a single large body. The Moon. Most planets in our solar system don't have a moon anywhere near this size relative to their own. Mars has 2 tiny captured asteroids. Venus has none. Mercury has none. Earth's moon is enormous by comparison, roughly a quarter the diameter of Earth itself. For a long time, scientists thought the moon was interesting, but not essential. A feature, not a requirement. Then, researchers started looking more carefully at what the moon actually does for Earth. And the picture changed. The moon acts as a stabilizer. Earth spins on a tilted axis, currently leaning about 23 degrees off vertical. That tilt creates seasons. Without seasons, climate patterns would be very different. But the more important effect is what prevents the tilt from changing wildly over time. Computer models show that without the moon's gravitational influence, Earth's axial tilt could swing dramatically, perhaps all the way to 90 degrees over millions of years. A tilt that extreme would mean the poles pointing directly at the star for months at a time, followed by complete darkness. The climate swings would be violent. Stable, long-term conditions for complex life to evolve would be far harder to maintain. The moon locks Earth's tilt within a relatively narrow range. It acts as a massive counterweight in the sky, damping the wobble that would otherwise destabilize the planet's climate over geological timescales. There's more. The moon drives tidal forces on Earth. Those tides have influenced the chemistry of coastline environments for billions of years. Some scientists believe that the rhythmic flooding and draining of coastal zones, driven by tidal cycles, played a role in early chemical evolution by concentrating and mixing organic molecules in ways that inland water bodies couldn't replicate. And the moon has slowly moved away from Earth over billions of years, gradually reducing those tidal forces. This gradual change may have gently shifted early life into different environments at just the right pace. Whether all of this was truly necessary for life to reach intelligence is still debated. But the pattern is unsettling. Each time scientists look at one of Earth's unique features, they find it doing something important. And each unique feature was the product of a specific, improbable event. A planet that formed in the exact right zone, got hit by a large impactor at just the right angle, developed plate tectonics that lasted billions of years, kept a stable tilt, maintained a magnetic field that blocked radiation, stayed wet, and did all of this long enough for life to crawl from simple chemistry to something that could ask why it exists. The question growing in the back of every researcher's mind is an uncomfortable one. Is this list of requirements so long and so specific that we might be genuinely rare? And if we are rare, how rare? Is there one civilization in the galaxy? A handful? Or are we entirely alone across the observable universe? To answer that, scientists looked at the one thing they could study directly. Time, and what they found about timing, made the loneliness feel even more profound. Imagine the entire history of the universe compressed into a single year. The universe begins on January 1st. Our solar system forms in early September. The first multicellular life appears in November. Dinosaurs come and go in the middle of December. Modern humans appear on December 31st, in the final hours of the year. Human civilization, agriculture, writing, cities, all of recorded history, fits into the last few seconds before midnight. We have been scanning the sky for alien signals for about 60 years. On that calendar, 60 years is less than a fraction of the final second of December 31st. That's the listening window we've opened so far. But it gets more specific than that. When we listen, we're listening for radio signals. Radio technology itself is only about 130 years old on Earth. Our strongest deliberate broadcasts have been travelling through space for about 60 years. The bubble of radio noise we've created around Earth stretches roughly 60 light-years in every direction. 60 light-years in a galaxy 100,000 light-years wide. If you shrank our galaxy to the size of a football field, our radio bubble would be smaller than a single grain of sand. Every star system outside that tiny bubble has received zero evidence that humans exist. No signal has reached them, no proof of our technology. From the perspective of the vast majority of the galaxy, Earth remains a silent, unremarkable world. Now flip the scenario. Suppose an alien civilization 1,000 light-years away has been broadcasting signals for 10,000 years and then stopped. We would need to start listening in that exact 1,000-year window when the signal was in transit past our location. Miss that window by a few hundred years in either direction, and we get nothing, even though they were actively broadcasting. The universe has been running for 13.8 billion years. Civilizations could have risen, transmitted, and gone completely silent long before the first human being ever drew a picture on a cave wall. A civilization that flourished 2 billion years ago and broadcast for 1 million years would have finished sending signals roughly 1,900,000,000 years before we started listening. Their signal swept past the location where Earth now orbits and kept travelling outward, long before our planet even formed. That signal is now somewhere deep in intergalactic space, spreading thinner with every passing year, carrying proof of a dead civilization that no one alive will ever know about. And we, in turn, have been broadcasting for 60 years. A civilization 200 light-years away hasn't received our signals yet. They might not for another 140 years. If they happen to be looking in the right direction at exactly the right moment when our signal arrives, they'd detect a faint, spreading bubble of television and radar noise emerging from an ordinary star. They'd have to be paying very specific attention. And they'd have to be there, alive, technologically capable, and listening at the precise moment our signal arrives. The timing problem alone might account for much of the silence. 2 civilizations have to exist at the same time, within a manageable distance, both listening, both transmitting, and both pointed in the right direction at the right moment. And yet, some scientists argue the timing isn't the main issue, because something else about our broadcasts makes them even harder to detect than most people realise. For decades, a common idea in the search for alien life was that our radio signals were leaking outward into space, creating a growing sphere of noise that any sufficiently advanced civilization might pick up. Movies have been made around this concept. Scientists debated it. It felt like a reason for hope. The reality is more sobering. Radio signals spread out in all directions as they travel, and as they spread, they weaken. The energy gets diluted across a larger and larger surface with every light year of distance. Physicists describe this as the inverse square law. If a signal travels twice as far, it becomes 4 times weaker. 3 times as far, 9 times weaker. The signal doesn't just fade gently, it collapses. Our television broadcasts, radio shows, and early radar pulses are all spreading outward right now. By the time those signals reach even the nearest star systems, just 4 to 5 light-years away, they are already far too weak to be detected by any antenna we know how to build. A radio telescope pointed at Alpha Centauri, the nearest star system, trying to pick up Earth's broadcast television signals from that distance would need to be vastly more sensitive than any instrument we've ever constructed. The signals are there technically, but they are buried in noise. In practice, they are undetectable. This means our accidental leakage, all the noise of 100 years of broadcasting, is already invisible to anything outside our immediate neighbourhood. What might actually be detectable from a distance is a deliberate, highly focused transmission. A beam pointed at a specific target, using a large antenna, broadcasting at high power over a narrow frequency range. Scientists have sent a few of these deliberately. One famous example was the Arecibo message, a short binary code sent in 1974 toward a cluster of stars 25,000 light-years away. That message is still travelling. It won't arrive for roughly 24,000 more years, and it has no guarantee of being recognised as anything meaningful if anyone ever receives it. The calculation works in reverse too. Any civilization broadcasting its own noise into space faces the same problem. Their accidental leakage would fade long before it crossed the galaxy. For us to detect it, they'd need to be sending a deliberate, focused beam in our direction, and they'd have to be doing it right now, at this moment in history, aimed at our star, with no guarantee we exist or are listening. This is one possible explanation for the silence that doesn't require life to be rare. Maybe civilizations don't broadcast widely at all. Maybe they use tight, targeted communication that doesn't spray signals everywhere. The universe might be full of deliberate, narrowly aimed conversations between civilizations that have found each other, and we simply aren't on the contact list. We're listening for a shout. They might only be whispering to specific addresses. Or it might be something stranger than that. Some researchers have proposed that the silence is deliberate, that advanced civilizations know exactly who is out there, and they're choosing very carefully who they respond to. The reason why points to something deeply unsettling about what intelligence might do when it reaches a certain level of power. Consider the possibility that we are not being ignored because we're too far away or too hard to detect. Consider the possibility that we are being ignored on purpose. The zoo hypothesis proposes exactly that. Some researchers suggest that advanced civilizations are perfectly aware that Earth exists and harbours intelligent life. They see our radio signals. They may have observed us for thousands of years, and they have chosen, deliberately and consistently, to stay silent and hidden. The analogy is the nature reserve. Humans build protected areas where animals live without interference. We observe. We study. We occasionally feel the temptation to intervene. But the policy is non-interference. The animals live their lives without knowing they're being watched. According to the zoo hypothesis, Earth might be exactly that. A watched world, a reserve. A planet that advanced civilizations have agreed to leave alone, allowing its inhabitants to develop naturally without external contact. The idea was first proposed by astronomer John Ball in 1973. Ball suggested that the silence itself might be evidence of this policy. If advanced civilizations existed and wanted us to know about them, we'd know by now. Their technology would make contact trivially easy. The silence requires explanation, and one explanation is that it's chosen. This creates a deeply strange picture. Every night you look at the sky and see nothing moving, no lights blinking in patterns, no signals resolving from the static, and one possible reason is that whoever is out there is very, very good at hiding. There's a version of this idea with sharper edges. Some researchers have noted that maintaining a consistent silence across multiple civilizations would require coordination. If the zoo policy is real, it implies that advanced civilizations have found each other, communicated, and agreed to a shared rule about leaving younger species alone. That kind of coordination implies a level of organization among alien civilizations that we can barely imagine. A community of intelligences, scattered across the galaxy, maintaining a consistent policy toward every young species they encounter. And what triggers contact? Some versions of the hypothesis suggest that civilizations are only contacted when they reach a certain technological or ethical threshold. Others suggest the zoo policy never breaks. The reserve is permanent. What makes this uncomfortable is that it can't be easily tested. If the silence is real, it looks the same whether no one is there or everyone is hiding. The hypothesis is almost impossible to disprove. But there is a version of the silence that goes much further than observation and restraint. A version where the reason for hiding has nothing to do with protecting younger species. A version where silence is the only rational survival strategy. And in that version, the universe itself is the most dangerous place imaginable. Picture a forest at night. Completely dark. You can't see more than a few feet in any direction. You know other things are in the forest with you. You can hear the occasional snap of a branch, a distant sound that might be breathing, and you know with certainty that some of those things are predators. What do? You stay silent. You kill your flashlight. You move as quietly as possible and hope nothing has already found you. The dark forest theory applies that same logic to the entire universe, and once you hear the argument, it's hard to dismiss. The theory was developed by Chinese author and physicist Lu Cixin, drawing on ideas from game theory and evolutionary biology. The core argument goes like this. Every civilization needs resources to survive. Resources are finite. Technology grows, meaning resource consumption grows, and across the timescales of the universe, every civilization will eventually face scarcity. Now add one more ingredient. You can never fully trust another civilization. Even if a species seems friendly at first contact, you can't verify their true intentions. You can't see inside their decision-making. You don't know what they'll want in 1,000 years, when their resource needs might be very different from today. And because the distances involved are so vast, any conflict happens in slow motion. By the time you detect a threat, it might already be too late to respond. Given those conditions, the game theory calculation becomes brutal. The safest strategy is always to eliminate any potential rival before they eliminate you. Contact is risk. Silence is survival. Any civilization that announces its presence is handing its location to every other player in the game. Under this framework, a galaxy full of intelligent life would look exactly like the one we observe. Silent, dark, every civilization either hiding or already gone. The really disturbing part is that the theory doesn't require civilizations to be evil or violent. It requires only that they be rational. Given incomplete information and unlimited potential stakes, the logical move is always to act first. This explains why we haven't been contacted in a way the zoo hypothesis doesn't. The zoo hypothesis requires benevolence. Patience, restraint, the dark forest requires nothing except cold logic. And some researchers take it a step further. If the dark forest is real, then our broadcasts were a catastrophic mistake. Every radar pulse, every television signal, every deliberate message we've beamed into space has been broadcasting our location for decades. We've been screaming into the dark. And something might have heard. That's speculation, obviously. The dark forest theory is a framework for thinking about the problem, not a confirmed fact. But it is internally consistent in a way that makes it deeply uncomfortable to dismiss entirely. What none of these theories address is a simpler possibility. Maybe civilizations aren't hiding. Maybe they're gone. Not destroyed by others, but transformed into something so different from what they started as that they left no trace we'd recognize. Some scientists think the most advanced civilizations in the universe might have stopped existing in any form we'd understand thousands of years ago. Every search for alien life so far has followed the same basic assumption. Aliens communicate with radio waves, the same way we do. Radio travels at the speed of light, penetrates most of the galaxy, and requires technology that a civilization at our level can produce. It seemed like the logical guess. But what if it's wrong? Radio technology on Earth is about 130 years old. We used horses as our main form of transportation a mere 200 years ago. In the span of a universe that has been running for 13.8 billion years, we are almost incomprehensibly new. Any civilization older than us by even a few thousand years, let alone millions, would have moved past radio the way we moved past smoke signals. Think about the jump from our great-grandparents' era to today. They communicated by telegram and letter. We carry devices in our pockets that stream live video from anywhere on Earth. That change happened in roughly 100 years. Extrapolate that rate of technological change across 1,000,000 years and radio becomes laughably primitive. Advanced civilizations might communicate using neutrinos. These are subatomic particles that pass through almost all matter with no interaction whatsoever. A neutrino beam can travel straight through a planet without slowing down. If a civilization figured out how to encode information in neutrino streams, they could transmit through solid objects, through entire star systems, without any possibility of the signal being intercepted or scattered by interstellar gas and dust. We have no practical way to detect neutrino-based communication at interstellar distances. Our current neutrino detectors are underground tanks filled with water, designed to catch the rare occasion when a neutrino interacts with something. Detecting a controlled neutrino signal from light years away is far beyond any technology we currently have. Quantum entanglement is another possibility that comes up in theoretical discussions. Entanglement is a phenomenon where two particles become linked so that measuring one instantly affects the other, regardless of distance. Some scientists have speculated that advanced civilizations might find a way to use this for communication across vast distances. Current physics says this can't transmit information faster than light. But current physics is what we know today. Laser communication is another option. Tight, focused beams of light in specific wavelengths, sent between specific targets, carry enormous amounts of information very efficiently. They're nearly invisible from any direction except exactly where they're pointed. A galaxy full of laser communicating civilizations would appear radio silent to anyone who wasn't already in the network. There are even more exotic ideas. Gravitational waves, ripples in space itself caused by massive objects, carry energy across the universe. A civilization advanced enough to generate controlled gravitational wave signals would have a communication method that passes through everything. We only recently developed the ability to detect natural gravitational waves, and that required instruments measuring changes smaller than 1,000th the diameter of a proton. The uncomfortable truth is that we're listening with ears tuned to one specific frequency, in one corner of the electromagnetic spectrum, using technology that is a few decades old, and we're searching for civilizations that might be millions of years ahead of us. That gap in sophistication is almost impossible to fully appreciate, but it matters. Because the silence we hear might say less about how empty the universe is, and more about how limited our instruments currently are. And what if someone out there has already built something so large, so unmistakably artificial, that our telescopes should be able to see it directly? It turns out we may have already found exactly that, and the explanation we're missing is still nowhere in sight. In 2015, astronomers noticed something strange about a star roughly 1,400 light-years from Earth in the constellation Cygnus. Most stars dim slightly and regularly when a planet passes in front of them. The dimming is small, predictable, and repeats on a fixed schedule as the planet completes its orbit. This is how scientists have found thousands of planets in other star systems. This particular star dimmed differently. Its brightness dropped by up to 22% at irregular intervals. The dimming lasted for days at a time and then disappeared completely. Then it came back in a different pattern. Then disappeared again. 22% is enormous. A planet large enough to block that much starlight would have to be several times the size of Jupiter. Planets that size at that orbital distance don't form naturally. And the irregular, unpredictable timing matched no planetary orbit model that astronomers could construct. Scientists called it KIC 8462852. The internet quickly gave it a more memorable name, Tabby's star, after the lead researcher who brought it to wide attention. The explanations that followed range from mundane to extraordinary. One early suggestion was a swarm of comets, a dense cluster of icy bodies passing in front of the star at irregular intervals might block varying amounts of its light. But the sheer amount of dimming and the lack of any infrared heat signature that a comet swarm would produce made this explanation feel incomplete. The infrared problem was significant. Anything physical blocking the starlight would absorb some of that energy and re-emit it as heat. Telescopes sensitive to infrared light should detect that heat. They found far less than expected for any solid material large enough to cause the observed dimming. One researcher proposed the possibility that captured attention around the world. What if the dimming was caused by a megastructure, a massive artificial construction built by an advanced civilization to harvest energy from the star, a partial shell of panels collected around the star to capture its output, something built, assembled and maintained by an intelligence that had been developing for millions of years. A construction like this, called a Dyson structure after physicist Freeman Dyson, who first proposed the concept in the 1960s, would explain the irregular dimming. Different panels at different orbital distances would block light on different schedules. The absence of a strong infrared signature might suggest the captured energy was being used efficiently rather than wasted as heat. Scientists were careful. The megastructure hypothesis was listed as a possible explanation alongside the comet swarm, unusual dust clouds, and other natural scenarios, but the star continued to behave strangely. Follow-up observations found that it was slowly dimming overall across multiple years, a behaviour that added another layer of mystery. As of the most recent data, Tabby's star remains unexplained. No single natural model fully accounts for everything observed. The megastructure hypothesis remains on the table, unconfirmed and unrefuted. And it isn't the only strange signal researchers have found. 47 years before Tabby's star captured headlines, a radio telescope in Ohio picked up something so unusual that a scientist wrote one word on the printout when he saw it. That word became the name of one of the most famous unsolved mysteries in the history of the search for alien life. On August 15th, 1977, a radio telescope called the Big Ear, operated by Ohio State University, was scanning the sky as part of an ongoing search for signals from other civilizations. Astronomer Jerry Eman was reviewing the printed data several days later. He was going through long columns of numbers, looking for anything that stood out from the background noise of space. Most of the readout was unremarkable, static, random variation, the ordinary hiss of the cosmos. Then he saw it. A column of characters that registered a signal 6 times stronger than anything expected from background noise. It lasted exactly 72 seconds, which was the maximum amount of time the Big Ear telescope could observe any fixed point in the sky as Earth rotated. The signal appeared, hit its peak, and faded exactly as a genuine extraterrestrial narrowband radio signal would behave. Eman circled the printout in red pen and wrote a single word in the margin. Wow. The signal, which scientists now call the WOW signal, has never been fully explained. It appeared once. Astronomers pointed every available instrument back at the same patch of sky. They listened again and again over the following decades. The signal never returned. The characteristics of the WOW signal were striking. It appeared near a frequency of 1420 MHz, which is the natural frequency emitted by hydrogen atoms, the most common element in the universe. Many researchers searching for alien signals had specifically chosen this frequency to listen to, reasoning that any civilization wanting to make contact would pick a frequency that any other civilization with basic radio astronomy would recognize. The signal came from the direction of the constellation Sagittarius. It showed no signs of a terrestrial origin. It wasn't a reflection from a satellite or an aircraft. Its frequency shift, the way it varied slightly as if coming from a fixed point in space while Earth rotated, matched what would be expected from a signal originating far beyond our solar system. But it had no detectable information encoded in it, no repeating pattern. no structure that suggested a deliberate message beyond the signal itself. Attempts to explain the WOW signal naturally have included a comet releasing a sudden burst of hydrogen gas, a possibility some researchers proposed in 2017 based on the position of two comets at the time. But other astronomers contested this explanation, arguing that comets don't produce signals with the observed characteristics. The mystery remains open. What makes the WOW signal significant beyond its specific characteristics is what it represents. It was one moment, in one location, for one brief window of time. And it was unlike anything before or since. If it was artificial, the civilization that sent it may no longer exist. Or they sent it once as a beacon and stopped. Or they sent it continuously but aimed it like a lighthouse beam, and our planet only briefly passed through its sweep. Every year that passes without a repeat makes the natural explanation seem slightly more likely, and the artificial one slightly harder to confirm. The uncertainty is the thing that never goes away. And some scientists argue that if advanced civilizations do exist, they may have stopped using any form of external communication at all. The reason why suggests a future for intelligence that is stranger than anything humans have yet imagined. Every story about finding alien life assumes that advanced civilizations want to be found. They build bigger telescopes. They send more powerful signals. They launch ships toward distant stars. They reach outward, the way we imagine ourselves doing someday. But there's a theory that says the opposite happens. That sufficiently advanced civilizations stop reaching outward entirely and turn inward instead. The idea is called the transcension hypothesis. It was formalized by futurist John Smart in the early 2000s. The argument goes like this. As technology advances, the most efficient use of energy and intelligence shifts from exploring vast physical space to exploring the much richer space of complexity within small volumes. Instead of spreading across the galaxy, the most advanced civilizations compress themselves into increasingly dense, efficient systems. Think about the trajectory of computing on Earth. Early computers filled entire rooms. Then they fit on desks. Then in pockets. The smartphone in your hand contains more computing power than the entire combined processing capacity of NASA when it first landed humans on the moon. And that compression trend has continued consistently for decades. Now extrapolate that forward a million years. The most powerful information processing systems would be extraordinarily small, extraordinarily dense, and extraordinarily energy efficient. A civilization at that level of development might fit its entire intellectual and social life into a volume the size of a city block while running simulations of complexity that dwarf the physical universe in richness and detail. Why would such a civilization bother with the slow, cold, empty physical universe? What does physical space offer that a sufficiently advanced internal simulation doesn't? The answer might be nothing. Under the transcension hypothesis, civilizations that reach a high enough technological level essentially disappear from the observable universe. They collapse inward. They build virtual realities of staggering depth. They run experiments in simulated physics. They experience entire histories inside compressed computational substrates. And from the outside, they look like nothing. No radio signals, no megastructures, no ships crossing the galaxy. Just silence where a civilization used to be. This hypothesis is compatible with the Fermi paradox in a way that requires no filter and no destruction. Civilizations don't die, they graduate. They move to a different mode of existence that we can't detect with any instrument currently aimed at the sky. Some scientists find this deeply unsatisfying. It replaces one mystery with another and leaves no way to test it. Others find it plausible because it matches a direction that Earth's own technology is clearly moving. Virtual reality, neural interfaces, artificial intelligence, computational simulation. All of these point toward a future where the richest experiences are not in physical space but in constructed environments of increasing sophistication. The question this raises for the search for alien life is uncomfortable. If the end state of intelligence is to go invisible, then the universe might be full of post-physical civilizations right now, undetectable and completely uninterested in contact. And if that's true, finding another civilization before it crosses that threshold would require extraordinary timing. Timing, as it turns out, is the most brutal problem of all, because even if civilizations exist right now, the odds that two of them share a window of mutual detectability may be almost impossibly small. Right now, somewhere in space, a message is travelling. It left its source roughly 200,000 years ago. The civilization that sent it, if it was sent deliberately, did so when modern humans were just beginning to exist on Earth. They lit a fire, if you will, before we ever had the capacity to see light at all. That signal is still crossing the dark, slower than the expansion of space, faster than any physical object, spreading out as it goes, thinning with distance, carrying whatever information it holds across a galaxy that has changed enormously since the moment of transmission. And we have been listening for 60 years. This mismatch in timing is so fundamental that it barely gets the attention it deserves. Our listening window is 60 years long. The signals crossing the galaxy right now were generated by civilizations that may have existed hundreds of thousands or millions of years ago. The ones being generated by civilizations alive today won't reach Earth for thousands of years. We are trying to catch a river with a cup held open for 30 seconds. Here's a specific way to feel the scale of this. The star system Tau Ceti sits about 12 light-years from Earth. It's one of the nearby candidates scientists sometimes discuss as a potential host for habitable planets. The civilization there, if one exists, sent signals toward Earth that would have left Tau Ceti 12 years ago to arrive now. If they started broadcasting when our own radio era began, in the early 1900s, their signals are currently about 120 light-years into space, nowhere near us. For us to hear them right now, they would have had to start broadcasting in our direction, by coincidence or by observation of Earth, at least 12 years ago. And we would have needed to already be listening and pointed in exactly the right direction. Scale that scenario across thousands of star systems, and the probability of simultaneous listening and transmitting in the same corridor of space collapses quickly. Some researchers have proposed a different approach entirely. Instead of broadcasting into empty space and hoping, they suggest we identify the most likely candidate planets, the ones in the right zone around the right stars, and focus all of our listening power on those specific targets. A targeted search rather than a general scan. This is more or less what some modern programs now do. Advanced telescopes lock onto specific stars and listen for patterns in radio frequencies, laser pulses, or other signals that can't be produced naturally. The list of targets keeps growing as new planet-finding missions discover more candidates. But even targeted listening faces the timing problem. A civilization that broadcast for 1 million years and then stopped is silent today, even if their signals saturated our galaxy for most of that time. What no search program has found, in any frequency, from any direction, in any observing run, is a repeating structured signal from beyond our solar system that can't be explained by natural physics. 60 years in, thousands of stars checked, complete silence, and yet scientists keep searching, because the universe has one more trick that nobody accounted for in the early equations, a trick related to when in the universe's history life is most likely to appear. Two civilizations can exist at the same time. They can be close enough to communicate, and they can still miss each other completely. That's the overlap problem, and it might be the single most underappreciated reason why the universe feels empty. Think about it in human terms first. Imagine two people, strangers, living in the same city. They never meet. They shop at different stores. They work different hours. They walk different streets. The city has millions of people, but the chance of two specific individuals crossing paths at a specific moment is very small. Now scale that up to civilizations spread across a galaxy. Two intelligent species can be separated by 10,000 light-years and still technically be neighbours on a galactic map. But they have to exist at the same time, be transmitting at the same time, transmitting toward each other, and have both built technology capable of detection, all simultaneously. The universe has been running for 13.8 billion years. Our galaxy has been producing stars for most of that time. Civilizations could have emerged and collapsed hundreds of thousands of times during periods when Earth was still a molten rock. If the average lifespan of a technological civilization is 10,000 years, which is generous given our own uncertain trajectory, then civilizations are like sparks in a fireplace, each one brief, bright, and separated from the others by enormous stretches of dark. Even if the Milky Way has hosted thousands of civilizations over its lifetime, the chance that two of them are alive at the same moment and within communication range is a very different calculation than simply counting how many ever existed. The Drake equation includes a variable for this, the letter L, representing how long a civilization broadcasts detectable signals. Frank Drake himself emphasized that L might be the most important variable in the entire equation. If civilizations tend to broadcast for 1 million years, the galaxy should be full of overlapping signals right now. If they broadcast for 1,000 years and go quiet, the windows barely overlap. Modern researchers have refined these estimates. Some argue that civilizations capable of interstellar communication might exist in the galaxy right now, but the expected distance to the nearest one, given conservative survival assumptions, might still be tens of thousands of light-years. Close enough to communicate, in theory, but separated by a delay of tens of thousands of years. Any conversation spanning that distance would outlast our entire recorded civilization many times over. And this is before accounting for the possibility that civilizations change their communication methods over time, phasing out radio just as we're beginning to search for it. The overlap problem doesn't require life to be rare. It allows for a universe full of life and still produces exactly the silence we observe. Ships that passed each other in the night, broadcasts that swept across empty space at the wrong moment, signals that arrived before we were listening or after we stopped. But there's one additional factor that scientists have started to take seriously only recently. The universe's age may actually work against contact in a more specific way than the timing problem suggests, because the conditions for intelligent life may only have become possible relatively recently, and we might be arriving at the very beginning of the era when intelligence can exist, not the middle. Most people take the moon for granted. It rises, it sets, it pulls the tides. It's been there for as long as anyone can remember, and it feels like a permanent and unremarkable feature of the sky. But Earth's moon is genuinely strange, and the more scientists study what it does, the more they suspect it might be a rare gift that made our existence possible. The moon formed from a violent collision early in Earth's history, as described in an earlier chapter. What makes it remarkable isn't just its size, but its precise effect on Earth's behaviour over geological time. Earth tilts on its axis at about 23 degrees. That tilt creates the seasons we experience every year. Spring, summer, autumn, winter, all driven by how much of Earth's surface faces toward or away from its star at different points in the orbit. Without that tilt, the planet would have almost no seasonal variation. The tropics would bake constantly, and the poles would freeze permanently. Climates would become extreme and static. Now here's the critical part. That tilt could wander. Without the moon's gravitational anchor, simulations show that Earth's axial tilt might drift anywhere from nearly 0 degrees to nearly 90 degrees over millions of years. At 90 degrees, one pole would point directly at the star for half the year. The surface temperatures would swing violently. Ice ages would come and go not over tens of thousands of years, but over millions of years, with extremes far more severe than anything in Earth's actual history. Complex life needs time to adapt. When environments swing too wildly and too fast, species go extinct faster than evolution can respond. The moon's stabilizing influence may have kept Earth's climate variable but manageable, allowing long periods of relative stability during which complex ecosystems could develop and persist. Now look at other planets. Mars has no large moon. Mars's axial tilt wanders significantly over millions of years. Climate models for Mars show that its poles have pointed more directly at the star in the geologic past, causing dramatic shifts in ice coverage and atmospheric pressure. One of the reasons Mars lost its liquid water may be connected to the chaotic swings in its orbit and tilt over time. Venus has no large moon either. It rotates so slowly that a single day on Venus is longer than its year. Its tilt is minimal, which produces almost no seasons, but it also means no moderating cycle of heat redistribution across the planet's surface. Earth's moon stabilizes the tilt. The tilt creates seasons. The seasons drive climate patterns that cycle nutrients and water across the planet. That cycling helped life spread into every corner of the globe, from deep oceans to mountaintops. The chain of dependencies is long, and somewhere in that chain, researchers suspect, the moon might be a critical link. Finding a planet with a large stabilizing moon orbiting in the right zone around the right star, with plate tectonics and liquid water, is a combination of circumstances that may be extraordinarily rare across the galaxy. Each new requirement added to the list makes intelligent life look more like a cosmic coincidence. But scientists found one more large-scale hazard that would have sterilized most of the universe's history entirely. And understanding it changes how we think about when life can exist at all. For most of the universe's history, the cosmos was a far more violent place than it is today. Gamma-ray bursts are the most energetic explosions in the universe. A single burst releases more energy in a few seconds than our star will emit over its entire 10 billion year lifetime. They occur when massive stars collapse into black holes or when two dense stellar remnants collide. And they fire two narrow beams of radiation outward at nearly the speed of light. The radiation in those beams is lethal to life as we know it. If a gamma-ray burst fired within a few thousand light-years of a planet with a developing atmosphere, the blast would strip away the ozone layer, expose the surface to lethal levels of ultraviolet radiation, and trigger a mass extinction. The damage would persist for years. Here's the problem for early civilizations. The rate of gamma-ray bursts in the early universe was dramatically higher than it is today. Young galaxies were producing massive stars at a far greater rate. Massive stars burn fast, collapse violently, and generate these bursts with much higher frequency than the older, calmer stars that dominate galaxies today. For the first several billion years of the Milky Way's history, the galaxy's interior, the dense central regions where stars packed closely together, was almost certainly too dangerous for complex life to survive. Bursts were so frequent that any planet developing complex biology would face sterilizing events before multicellular life could gain a foothold. Only in the outer regions of galaxies, where star density was lower and bursts were rarer, did conditions become survivable. And only after several billion years, as the rate of new massive star formation declined, did the overall burst frequency drop to levels where a planet like Earth could develop complex life without being regularly wiped out. Earth sits in a relatively calm region of the Milky Way, far enough from the dense galactic center to have avoided the worst of this violence. Our position in the galaxy appears to be another non-trivial ingredient in the recipe for our existence. Researchers call this concept the Galactic habitable zone. Just as a planet needs to orbit at the right distance from its star to keep water liquid, a star needs to orbit the galaxy at the right distance from the galactic center to avoid radiation sterilization. Too close and gamma-ray bursts and other violent events pose constant threats. Too far from the center and the metal content of the gas and dust drops too low to form rocky planets with the heavy elements that life requires. Earth sits inside a relatively narrow band where both conditions are met. Enough heavy elements for complex chemistry, far enough from the galactic core to avoid frequent sterilization. And the timing matters enormously. The early universe was too violent. The very far future universe may be too cold and too sparse as stars burn out. There is a window, several billion years wide, when conditions in the right parts of galaxies become hospitable enough for intelligent life. We are inside that window. Barely, and some researchers have begun to argue that we may have arrived earlier than most. If that's true, what it implies about our place in the story of the universe is stranger than almost anything else we've encountered. Strip away everything comforting about the search for alien life. Remove the hopeful assumptions. Look at the checklist honestly. What do you need to produce a species capable of asking questions about the universe? You need a star the right size and age, stable enough to shine consistently for billions of years. Our star qualifies. Many don't. Stars much larger than ours burn out in millions of years, far too fast for complex life to develop. Stars much smaller may blast their close-orbiting planets with flares. You need a planet in the right orbital zone. Earth's orbit keeps liquid water on the surface. The zone is not enormously wide. Venus is just slightly too close. Mars is slightly too far. You need a planet the right size. Too small, and the planet can't hold a thick enough atmosphere. Too large, and it becomes a gas giant with no solid surface. You need plate tectonics running for billions of years. You need a large, stabilizing moon. You need a magnetic field strong enough to deflect solar radiation. You need the planet to form in the right region of the galaxy, far enough from the center to avoid frequent sterilization, but close enough to contain heavy elements. You need the right timing. The star and planet need to exist during the era when the galaxy is calm enough to allow life to persist without regular catastrophic interruptions. You need the initial spark of life itself, which still has no confirmed explanation. Scientists have made progress understanding how organic molecules form in space and how they behave in early ocean conditions. But the specific moment when chemistry became biology, when the first self-replicating molecule appeared, remains unknown. Then you need that life to make the leap from single cells to complex cells, which on Earth happened exactly once over billions of years. Then you need the complex cells to form multicellular organisms, then nervous systems, then brains large enough to process abstract thought, then a social structure capable of accumulating and transmitting knowledge across generations, then language, then writing, then science. Every one of those steps required specific conditions. Many of those conditions appear to be rare in the universe, and the steps happened in a sequence, each one enabling the next, across billions of years of geological and biological stability. The rare earth hypothesis, developed by scientists Peter Ward and Joe Kirschvink, argues that each of these conditions is independently improbable, and that the probability of all of them occurring together on a single planet is so low that Earth may be unique, or nearly unique, in the observable universe. Other scientists push back. They argue that life is more resilient than we think, that we've found organisms surviving in conditions we once considered impossible, in boiling acid, in the vacuum near hydrothermal vents, in the cores of nuclear reactors. Life finds a way, they say, and we shouldn't assume our specific conditions are the only ones that work. The debate is unresolved. But the longer the search continues without finding anything, the more weight the rare earth argument accumulates. And there's one final version of this idea that turns the loneliness completely around. A possibility that sounds almost too strange to take seriously, but that a number of serious researchers have begun to consider. What if we're not the remnants of an old universe full of failed civilizations? What if we're the beginning? The universe is 13.8 billion years old. That sounds like an almost unimaginable head start. But intelligent life requires specific ingredients. Those ingredients take time to assemble. Planets need heavy elements to form. Heavy elements don't exist at the beginning of the universe. They have to be forged inside stars and scattered by explosions when those stars die. The first generation of stars in the universe contained almost no heavy elements. They were made almost entirely of hydrogen and helium, the two elements that existed after the Big Bang. When those stars died, they seeded the universe with heavier atoms for the first time. A second generation of stars formed from that enriched material. When those stars died, they enriched the universe further. Each generation of stellar life and death added more of the raw materials that rocky planets and carbon-based chemistry require. Earth sits in a solar system containing a wide variety of heavy elements, from iron in the planet's core to carbon in every molecule of life. That abundance took billions of years of stellar recycling to produce. For most of the universe's first several billion years, the heavy element content of most regions of space was too low to form planets like Earth. The earliest rocky worlds were simpler, less chemically diverse, and less hospitable to the complex chemistry that life appears to require. Add the gamma-ray burst problem from earlier, the early universe was also far more violent. Frequent sterilizing explosions, higher stellar activity, and more chaotic galactic environments made the first half of the universe's existence a particularly hostile time for complex life. When you factor in both problems, the timeline for when intelligent life first becomes possible in the universe gets pushed significantly forward. Some researchers have calculated that the first planets capable of hosting complex life with the right heavy element content and low enough radiation hazard only began to appear roughly a few billion years before Earth itself formed. That's a narrow window. And we're sitting inside it. This has led a small but serious group of scientists to propose something genuinely radical. We may be early arrivals. The universe may be at the beginning of the era of intelligence, not the middle. Most civilizations that will ever exist haven't appeared yet. They're waiting for their stars to form, their planets to cool, and their chemistry to get started. If this is true, the silence isn't a sign that we're rare or that others have destroyed themselves. It's a sign that the universe is still young enough that few others have arrived. Our descendants, millions of years from now, might live in a much more populated cosmos. The lights are coming on, one star system at a time. We simply lit ours early. This idea is either deeply comforting or deeply isolating, depending on how you think about it. We're not late to a party everyone else already left. We might be the first guests to arrive, in a universe that hasn't yet filled up. What makes it stranger is that the evidence for it and the evidence against it both produce exactly the same observable universe, a quiet sky and a radio silence that gives nothing away. If the universe is filled with life, and has been for billions of years, it should be messy. Loud, overflowing with evidence. Civilizations don't just send radio signals, they change their environments. They consume energy. They modify their planetary chemistry. They produce waste products that get trapped in atmospheres. They build things. All of those activities leave traces, and we now have tools sensitive enough to detect some of those traces from light years away. A civilization that burns fossil fuels as we do, pumps carbon dioxide and a cocktail of other gases into its atmosphere. A civilization that develops chemistry-based industry releases compounds that wouldn't exist naturally. A civilization that harvests enormous amounts of energy from its star might leave an unusual infrared signature around that star as the captured energy eventually escapes as heat. Modern telescopes can analyze the atmospheric chemistry of planets in other star systems by studying how starlight changes as it passes through those atmospheres. The technique is called transmission spectroscopy. As a planet crosses in front of its star, the star's light filters through the planet's outer atmosphere. Different molecules absorb different wavelengths of that light. By studying which wavelengths are missing, astronomers can deduce what gases are present. This method has already detected water vapor, carbon dioxide, and methane in the atmospheres of planets dozens of light years away. The instruments are improving rapidly. Within the coming decades, some researchers believe we'll be able to detect the chemical signatures of biology and potentially even technology in the atmospheres of nearby Earth-like worlds. The list of things we're looking for has grown far beyond radio signals. Atmospheric pollution. Unusual heat signatures. the steady dimming pattern of a partial megastructure around a star, laser pulses in optical frequencies, structured signals in infrared, anomalous gravitational signatures that might indicate engineered objects of enormous mass. Scientists have scanned thousands of stars across multiple search programs. The results, across all of these methods and all of these targets, are consistent. Nothing found. Every star checked has returned a natural signature. No unusual atmospheric chemistry pointing toward industry. No megastructures blocking starlight with an artificial pattern. No repeating signals in any frequency. No gravitational anomalies suggesting engineered objects. The universe, searched at every wavelength we know how to use, looks exactly like it would if Earth were the only technological civilization in it. This doesn't prove we're alone. We've checked thousands of stars out of 400 billion in our galaxy alone. The sample size is a fraction of a fraction. We've been doing this seriously for 60 years. We're using technology that a million-year-old civilization would find primitive. But the silence across so many methods, over so many targets, for so many years, is something that demands explanation. And every explanation leads somewhere strange. Either life is rare, or intelligence is rare, or intelligence is short-lived, or we're being hidden from, or we're simply looking wrong. Each option changes what it means to be here, alive, asking the question. 1,400 light-years from Earth, a planet called K218b orbits a dim red star. Scientists recently pointed the most powerful space telescope ever built at that planet and analysed the light passing through its atmosphere. What they found caused immediate debate. The chemical signatures suggested the possible presence of a compound called dimethyl sulfide. On Earth, dimethyl sulfide is produced almost exclusively by marine life, specifically by certain types of ocean microorganisms. It doesn't form in large quantities through geology or chemistry alone. The scientists who published the result were careful. The signal was weak. The detection needed confirmation. Other explanations might exist that hadn't been fully explored. Caution was required. But the implication was clear enough that the paper triggered a global conversation. If confirmed, it would be the first detection of a potential biological chemical signature on a world orbiting another star. As of the most recent data, the result remains unconfirmed. Follow-up observations are ongoing. What this moment illustrated is how rapidly the search has changed. A decade ago, detecting anything about the atmosphere of a planet 1,400 light-years away was impossible. Today, we can do it. Imperfectly, but genuinely. And the technology is improving every year. Space telescopes now in operation and under development are designed specifically to scan nearby Earth-like planets for biological markers. The list of target molecules goes beyond dimethyl sulfide. Scientists look for oxygen in combination with methane, a pairing that shouldn't coexist naturally without constant biological replenishment. They look for ozone signatures, phosphine in atmospheres where it shouldn't form, nitrous oxide produced by microbial activity. The first confirmed detection of any of these signatures on a world beyond our solar system would be one of the most significant events in human history. It would instantly and permanently change the Fermi paradox. If life exists at 1,400 light-years and also arose here, it becomes very hard to argue that intelligence is anything but widespread. But confirmation hasn't come. Each candidate signal so far has either been retracted, downgraded, or left in an unresolved state pending more data. Meanwhile, within our own solar system, missions are drilling into the ice shells of moons around Jupiter and Saturn, searching for simple life in the oceans believed to exist beneath. Mars rovers continue analysing soil samples for chemical traces of ancient biology. Every one of these searches is a form of asking the same question from a different angle. Are we alone? And the answer, after decades of looking with increasingly powerful tools, remains stubbornly unclear. But the emotional weight of the question isn't just scientific. If we are alone, or nearly so, the implications go far beyond astronomy. What it means for the value of everything humans have ever created and thought and felt is something that changes the nature of the question entirely. Remove every other civilization from the universe. Make Earth the singular exception. Accept the possibility, for a moment, that everything alive and aware in the observable cosmos is right here. What follows from that? Every piece of music ever composed exists in exactly one place. Every story ever told, every painting finished, every meal cooked for someone you love, every moment of grief and joy and confusion that makes up a human life exists here and nowhere else. The universe has been running for 13.8 billion years. It contains 2 trillion galaxies. Inside those galaxies sit hundreds of billions of stars each. And across all of that, across all that time and space, the only place where something looked up and wondered about its own existence is a small rocky world in an unremarkable corner of one average galaxy. That makes every human experience simultaneously enormous and terrifyingly fragile. If there's no one else, then everything that has ever been thought or felt or created exists in a single thin layer of biology clinging to one planet. A large enough asteroid, a runaway greenhouse effect, a nuclear exchange, any one of a dozen catastrophic scenarios ends the only known chapter of consciousness in the observable universe. Permanently, there are no backups. No other civilizations to carry knowledge forward. No other minds to independently rediscover what we discovered, mourn what we lost, or continue what we started. Carl Sagan, who spent his career thinking about these questions, put it this way: we are the means by which the universe knows itself. If that's true, and if we're alone, the weight of that responsibility is immense. The universe's only window on itself is here. And it can close. Some people find this terrifying. Others find it clarifying in a strange way. If we're the only ones, then every good thing humans do matters more, not less. Every act of curiosity, every scientific discovery, every moment of connection between people carries a significance that's hard to calculate. But here's the thing that scientists keep coming back to. We don't actually know we're alone. 60 years of searching, a sample covering a tiny fraction of the galaxy. Using tools a fraction as advanced as what a developed civilization might use is not enough to conclude anything definitive. The silence is real. The absence of contact is real. That the universe is enormous and old and we have barely begun to look. And there's one more possibility that doesn't get discussed as often. One that sits between total isolation and a crowded cosmos. A possibility that is in some ways stranger than either extreme. There's a version of the universe that is neither empty nor reachable. One where life and intelligence exist across the galaxy, separated from each other by the same combination of distance, timing, and physics that we've been exploring this entire journey. Under this picture, the universe is full, just not connected. Hundreds of civilizations might exist right now in the Milky Way alone, some broadcasting into space, some hiding, some turned inward, some just beginning to develop radio technology, some already extinct. All separated by distances that prevent any practical contact within the lifetime of a civilization. They're there, they're real. And they're as unreachable as a voice shouted across the ocean. This picture doesn't resolve the loneliness, it deepens it. Because it means the universe has produced intelligence many times over and arranged things so that almost none of those intelligences can meaningfully interact. Each one experiences the cosmos as a solitary observer. Each one looks out and sees an apparently empty universe and draws its own conclusions about what that silence means. Some of those civilizations may have concluded they're alone. They may have stopped searching. Others may still be listening, directed at a different part of the sky, waiting for something that has no chance of arriving. And somewhere in there, separated from us by tens of thousands of light years and thousands of years of signal delay, is a world where another species is making its own music, asking its own questions, looking at the same night sky and wondering exactly what we wonder. The laws of physics as they stand today give us almost no way to bridge that gap in any practical sense. No known mechanism allows information to travel faster than light. No technology on our horizon can cross interstellar distances in less than thousands of generations. The isolation may be, for all practical purposes, permanent. Some scientists take this as a reason to focus energy here instead of outward. If contact is practically impossible, then the most important thing any civilization can do is manage its own survival. Avoid the filter, whatever it is. Avoid the patterns that seem to end civilizations before they reach the stars. Stay alive long enough to understand more of the picture. Others argue the opposite, that the search should intensify precisely because the stakes are so high. If even one signal arrives, everything changes. The proof that we're not alone transforms what it means to be human more completely than any other discovery in history would. But whether the universe is empty or full, whether we're alone or surrounded by unreachable neighbours, one question underlies everything, the one that Fermi asked, and that no one has fully answered. Why does it look this way? Why is a universe built to allow intelligence also built in a way that seems to guarantee isolation? Is it a coincidence? An oversight in the laws of physics? Or is it something more deliberate than any of us are comfortable considering? You are made of atoms forged inside dying stars. The iron in your blood was produced in a supernova explosion billions of years before Earth existed. The carbon in every cell of your body was assembled in the heart of a star that lived and died before our solar system formed. You are, in the most literal sense, made of the universe looking at itself. And you are asking whether anything else is looking back. The answer, after everything we've examined, is that we genuinely don't know. We have silence. We have math that says the silence shouldn't exist. We have a growing list of reasons why the conditions for intelligence might be rare. We have theories about civilizations hiding, evolving beyond physical existence, destroying themselves, or simply never emerging. None of these theories can be proven with what we currently have. All of them are consistent with a quiet sky. What we do know is this. Life appeared on Earth almost as soon as the planet could support it. That suggests chemistry wants to become biology wherever the conditions allow. Life survived mass extinctions, ice ages, and the shifting of continents. That suggests biology, once started, is stubbornly persistent. And then, once in the late history of a middling planet orbiting an average star in the outer reaches of an ordinary galaxy, matter became complex enough to develop awareness, language, mathematics, and the ability to wonder about things far beyond its immediate survival. That happened here. The question of whether it happened anywhere else in the observable universe remains genuinely open. If it did happen elsewhere, the walls are high, the distances are brutal, the timing problem is severe, the speed of light doesn't negotiate, and whatever filter exists has left the sky clean and empty for every civilization that has ever looked. If it didn't happen elsewhere, then the silence is its own kind of answer, one that places a weight on this planet and everything on it that words struggle to carry. But here's what feels important, beyond the science and the theories and the empty frequencies. The fact that we are here asking the question changes something. Most of the matter in the universe will never do what you are doing right now. Most of it will never form into something capable of curiosity. Most of it will orbit its star, weather its surface, and eventually scatter back into space without ever once wondering why. You are the rare exception. The planet you stand on is the rare exception. Whether you're one of billions of such exceptions, or the only one ever produced by a 13.8 billion-year-old universe, the improbability is staggering either way. The universe seems designed to keep civilizations from finding each other. The distances are too vast, the windows too narrow, the physics too uncompromising. And yet here we are, having crossed every filter behind us, looking out at a silent sky. Still asking. Maybe that's enough to keep asking a little longer.